Let's get this show started. Hello, everyone. Thank you all for joining. Welcome to In Rhythm Lightning Talks. I'm Parag Katkar, your host for tonight. I'm the head of consulting practices at In Rhythm, and we have several awesome lightning talks lined up for you in the upcoming weeks. Our lightning talks are hosted every Thursday at 5:15 p.m. Eastern Time. And each week, one of our practice area consultants speaks on the latest and greatest technology trends in the industry that will help you keep learning and growing in your career. And this week, Tarek Fadali, who is a passionate Java engineer with us, is going to talk about threads. He's going to go over what threads are, why do we need them, what are their drawbacks, what are the big challenges managing threads, and the best practices to handle them. So without further ado, let's get it started, Tarek.
Okay, can you hear me?
Yeah.
So I've been trying to get better at multi-threading for several years now, and every time I get a chance, I'm playing around with threads, and they can do some pretty subtle, hard to predict things sometimes. So I have a bunch of programs that I've written that demonstrate some of the issues you can run into. But first, let me start off with an overview. So first I'll go back to basics and talk about processes, and then from there, maybe a little bit about what threads are and why we have them, then some of the advantages and disadvantages. And then I'm not an expert on threads, so I can't, and the talk is, even if I were an expert, it's only a short talk, so I can't teach you threads today, but maybe I can teach you something about how to learn about threads. And then at the end, I can show you some of the programs I've written. We can run them, see what happens. So why do we need processes? So it's one of the most basic services that the operating system can give you. You need an environment in which to run a program. And you could try to set that up so that you can only run one program at a time, and the original computers probably did.
No more toys. हमने toys लिया भी नहीं, तो मैं आऊँ करो.
But we really want to be able to do more than one thing at once. That's the other thing that processes do for you. So why do we want to do more than one thing at a time? One reason could be performance. If you have more than one processor, then you can let each processor do its own thing, and then you can get more work done. And even if you have one processor, you have very slow things that happen, like maybe a disk read. So that's like a very long thing. So that's like waiting a week from the computer's point of view and doing nothing. So you may as well give the computer, the CPU, another task so it can make progress on the other task. So even for a single processor system, it's useful to be able to do more than one thing at once. It's also helps with the user experience. We like to be able to check our email in one application, and then a different process will run something else. You might be able to achieve something like that by some ad hoc type of thing where you have some monolithic process that tries to do everything, but it'd probably be a nightmare. It might not be so bad if you only had a couple things to do, but like a modern computer where you have all these different applications, you need some kind of systematic way of doing it. So that's what processes give you. Another way to think about it is, instead of writing a program that can walk and chew gum at the same time, you can just write a program that walks and write another program that chews gum, and then you run both of the programs. So it can simplify your life if you have to have two things that you need to be truly concurrent and running at the same time, doing two things at once. So what about threads? Why do we need threads? You can think about some of the same considerations, but within the context of a single program doing multiple things at once rather than many programs. So you can do a lot of the things that threads can do with processes, but a process is, or a thread is more lightweight, so it won't take up as much memory and other resources. You can share memory. Processes have separate memory, which helps them from colliding with each other. So it is sort of an advantage, but on the other hand, sometimes you might want to share the memory. So if you think of a word processor, maybe like you type some lines into the word processor and you have a new line, and then it has to recalculate. If it's some big book, now maybe all the text shifts to different pages and has to recalculate the whole thing. But you want to have one thread that might process the user input. So the thread, having multiple threads working on that same memory will help with the responsiveness. For example, like if you didn't have threads, you might have to, while it's doing that calculation to figure out which page things are on, it's going to be unresponsive to your keyboard input. So that's not going to be a good user experience. The same thing can happen with servers, multiple threads. If you have each request on a separate thread, then the server can respond to them. You get a good response time, and the users will be happy. So also libraries and frameworks can bring in threads. So even if you didn't sign up for threads, sometimes they can sneak in. Like I mentioned, for server frameworks like Spring Boot by default, it'll be a request per thread. So that, some people say that's kind of a bad way to deal with set up a server. Like Node.js tries to be single threaded, for example. There'll be some threads that are kind of under the hood, but so it's very common to do things using one thread per request. So it might help in that context to know about threads. And sometimes if you want to have a scheduled task, usually that brings in threads, like a scheduled executor or timer task. So for dealing with those types of things, you might not need to know about threads. And on top of that, threads, the issues that come up with threads can be sort of contagious. Maybe I can touch on that later, but the state can sort of leak from one part of the code to another part of the code. So can spread like a wildfire, like the issues that'll come up, like it's hard to kind of keep yourself safe from knowing about threads, from having to know about them for those reasons. So what are some of the drawbacks of threads? In a nutshell, it's just that they're hard. They can also hurt performance. If you're using unnecessary threads, will create some overhead. And then to solve the issues that come up, you might use locks, and that can also hurt performance. It can also introduce some hazards like safety and liveness hazards, which I'll demonstrate what those are when I get to my programs. So, and then they can also, so I've talked about how they can make your life simpler, make applications easier to understand, because you can sort of make each thread do one thing at a time. But it can also add complication because of these hazards, for one thing. But it all mostly boils down to threads being hard, because if they weren't hard, you could just use threads and it wouldn't, as long as your program works. It's not, you can make a program correct and use many threads. And so why are they hard? They can bring in non-deterministic behavior, so it's hard to predict. So it's not just that. So it wouldn't be so bad if it was just like a coin flip type of thing, where you run it once and it does one thing, and you run it another time and it does another thing. It's a really bad kind of non-determinism, that it may be that you're running your application and it's totally fine for 3 years, and then all of a sudden you get a certain amount of load and then you see this bug come up. Actually, one of my programs might illustrate how something like that might happen. So it can be subtle, non-deterministic in a way that sort of goes under your radar. They can be hard to test, hard to reproduce the bugs if they do occur. And you have to keep track of multiple things at once. So there are some ways you can try to tame those kind of difficulties. One thing is to focus on the higher level APIs. So people have thought a lot about threads and how to use them, and they've designed some APIs to make it easier. So in Java, for example, there's the concurrent collections, like concurrent hash map. And there's like the executor framework. So using those higher level APIs can make your life easier. Like if you tried to build everything from the lower level stuff like wait and notify, it's a lot harder, a lot more error prone. So that's one way to tackle it. Some other languages have some interesting things. I've heard Go is good for concurrency. I've looked a little bit into Rust, but what Rust is interesting because Rust tries to actually build in sort of compile time checking so that your code won't even compile if you have the multi-threading problems. So that's an interesting take on it. But it's nice to be able to understand how to manage them yourselves. And if you're working in Java, you have to know how to do it. Another component of my approach to learning about threads is to do hands-on experiments, which I'm going to show you. The reason for that, well, hands-on learning is always good. It's always a good way to learn, make things stick. But particularly with threading, like I can't really convince myself to take some of these issues seriously unless I can see it, run the program and actually see it in action. And the same thing goes for like convincing your coworkers to take these things seriously. I've had conversations like that, because like I said, you may run these types of bugs that you get with multi-threading. You may run your program 100 times and you don't see the bug, and then the 101st time you run it, now you see the bug. It's hard to convince other people to take it seriously, hard to convince yourself to take it seriously. So the hands-on experiments really help with that. There is a little bit of a limitation as far as that goes, that some of the issues are so subtle, I haven't been able to reproduce them. It may be sometimes it may be platform dependent, or some of the things, maybe some compiler optimization that causes the problem. A compiler might decide to execute things in a different order than you wrote them in, and that can cause some of these bugs. I haven't been able to reproduce that myself. I'm sure you could if you tried hard enough. But you might, so that's a caution. You might not be able to explore everything unless you work really hard at it. And there are also a bunch of design principles you can learn that to help tame some of these issues. The way that I can think about it, to kind of boil it down to a nutshell, it's basically that shared mutable state is your enemy in multi-threading. And a lot of the design principles boil down to that. So you can either face your enemy head on, or you can try to avoid your enemy. And so some of the design principles are based on avoiding your enemy. So avoiding your enemy means if your enemy is a shared mutable state, you can either avoid sharing or you can avoid mutation. So avoiding mutation means you'd make everything constant that you possibly can. So functional programming kind of goes along with that approach. And you can use immutable objects and things like that. So that makes multi-threading a bit easier, if possible. If that's not possible, you can avoid sharing the state. And so that's kind of what you want to do, is make sure that only one thread can touch that state. So there are things like thread local variables you can use for that. Otherwise, you just have to watch whenever you return a variable. If it's a primitive type, then it doesn't matter. But if it's an object, like anytime you're returning it, anytime you store it in a public field, there are various ways that a variable can sort of escape out of its scope from one thread and be accessible by other threads. So that's confinement techniques will help you keep things restricted to only one thread. And finally, if you can't avoid sharing and you can't avoid mutation, you have to face your enemy head on, the shared mutable state. Then you do have to share the state, but what happens then is that you have to take turns sharing the state. So each thread has to take its turn. The way you do that is you use locks. The locks are kind of heavyweight. In some cases, you could get away with atomic variables or volatile variables. That's sort of a lighter weight mechanism to do that. So there are a lot of more subtleties to it than that. Maybe in the Slack channel, I'll post my reference that I like for learning about threads in Java. It's Java Concurrency in Practice, I think is the title. So I'll post a link to it. And so it's good to learn about threads before you need it, because it may be, I know in my career, some of the nastiest bugs I've dealt with had to do with threads. So it's nice to be able to not have to learn it just in time for that. When you already have your bug that's pretty difficult to deal with, and then you have to learn threads on top of it. So it's just a risk factor. But so it's nice to make some extra time to study it beforehand, if you can. Mike was just telling me maybe it's a good thing if people if you have these badly behaving threads, because it gives you job security. So then there are more jobs fixing the threading problems. So I think I'm about ready to switch to my demo. So here I have this program here it's going to be 2 threads running at once. And each thread is just going to increment a counter. And it's going to do it a certain number of times. So this number of times here, I've set it equal to 10,000. And I'm just going to run it. So I have these 2 threads hitting the counter. And it should be that they both hit the counter 10,000 times. So it should add up to 20,000. So I ran it and we did get the expected result. We expected the counter to reach 2,000. It got hit, or 20,000, because each thread hit it 10,000 times. So that's behaving as expected so far. We'll run it again, same thing. Run it again, same thing. Run it again, same thing. So let's try a bigger number and see if we get anything interesting. So I'll set the number of times to 40,000. Now I'm going to run the counter, run the program again. It's got 80,000. Oh, and so now we got something different. So we got 75,634. So something weird happened now. And so this is because this count variable here, that counter variable that's shared mutable state. And the 2 threads are sort of competing for that state at once, and they're bumping into each other, and they're what can happen is maybe one of the threads will hit the counter like 5 times, and then the process or the thread scheduler will stop it and start the other one, and then it could hit the counter. But the problem is that it's this incrementing is really 2 different operations. The first is to read the value of the variable. And the second is to increment it. So what can happen is that the first thread reads the value and then gets stopped, and the other thread takes over. And then maybe they both will add a +1 to their value, and then one of the threads will set the count equal to the new value. And so you might end up with a count that's less than what you would expect if they were doing if they were just separately counting, and they got out of each other's way so that they didn't interfere with each other. Then it does a +1 and then gets out of the other thread's way. And then, so if you use locks, you can fix this problem. But you kind of see there the point that sometimes, like I had to tweak this program a bit, play around with the numbers in order to be able to even see the problem. Like these bugs can go under the radar. So let me do, so that demonstrates a safety hazard. You can also have liveness hazards. So in order to solve safety hazards, like I mentioned, you would use a lock usually. And locks can introduce liveness hazards. So what can happen there is you can have one thread, you have two different locks, let's say. And if you hold the locks in an inconsistent order, so like here in this program, I have one thread that's going to take the first lock and then take the second lock, and then the other thread does it in a different order, takes the second lock and then the first lock. It's an inconsistent order. So these threads, again, it's supposed to count to 8,000, but somehow I'm not getting the deadlock. Oh, there, this time I got it to deadlock. So it gets to the end. And so it wasn't happening every time. But finally you see that this program still is running. So a bunch of times it was able to finish to completion, but when I ran it enough times, the threads got in each other's way and they got deadlocked. So one thread is waiting for the other, so it can't make progress, but the other thread is waiting for the first thread, so it can't make progress. So you got a deadlock. And so those are liveness hazards. There are other similar, it doesn't actually have to be locked. Anytime if you hold a lock for a long time, like maybe you sleep while holding a lock, or you do some long running computation, you can get similar issues. It might not be a full deadlock, but it could be like a performance issue. So I've seen problems like that happen. So with that, I think that's everything. Are there any questions?